Go on. Today we will do 7.3 trigonometric substitution. Trig substitution. So last time we did trigonometric integral. Right now we do trigonometric substitution. Idea. We will connect the following ideas together. First one is sine squared theta plus cosine squared theta equals to 1. And the derivative of sine theta respect to theta is cosine theta. Okay, so we have this in mind later on. We can use 1 minus sine squared theta for cosine squared theta. We use x equals to a sine theta to substitute in this form, square root of a squared minus x squared. Yeah, let's talk about this first. There are two other substitutions later on, but let's talk about this first for now, because once you understand why we do this kind of substitution, then it will be easier to go on to the other type of trig substitutions. Now, suppose for example, I see the square root of 4 minus x squared, right? And let's do the integral. Integral of square root of 4 minus x squared dx. Then I will say, oh, you know what? Let x equals to 2 sine theta. What about doing part of 7.2 with sine ax cosine bx? Actually, you can just use formula for that. Okay, let me look back first. So 7.2, did I use a last time? I really thought I'm done with that already. Yeah, I'm done with that. I'm done with 7.2. Okay, so, well, anyway, suppose you have that concern about what happened with sine. Let me see your question again. Sine ax and cosine bx. So let's say, for example, we want to integrate integral of sine ax cosine bx dx. No, don't do integration by parts. I think you can, but why? I will use this formula. I know that sine theta cosine, no, don't use theta, sine x. Sine what? Sine a cosine b is equal to 1/2 sine of sum over 2 no, actually no, sine of sum only. Okay. Sine of sum plus sine of difference. Okay, so using that, then this is equals to 1/2 integral of sine ax plus bx plus sine ax minus bx dx. So that's equals to 1/2 integral of sine x times a plus b dx plus 1/2 integral of sine x times a minus b dx. This is equals to integral of sine is negative cosine. So that's 1 over a plus b, the coefficient, times negative cosine of a plus b x plus 1/2 1 over a minus b of negative cosine of a minus b of x. Don't forget plus constant. Okay, and let me distinguish a is not equals to b. Okay, because if a equals to b, this will be 0 already. Right? And they just double angle. Go on further, then this is equals to negative 1 over 2 of a plus b cosine a plus b of x minus 1 over 2 a minus b cosine a minus b of x plus constant. Yeah, something like that. Okay, basically I use that formula, one of the formula product to sum formulas. Okay, for 7.2, the one that I didn't cover, that's because all you need to do is actually applying that formula. So do I answer your question? Okay. Now 7.3, go back to 7.3. Now, why do I use this substitute that x by 2 sine theta? Because of the following. If x equals to 2 sine theta, then 4 minus x squared will be 4 minus 4 sine squared theta. Okay, now the purpose is I try to match to get 1 minus sine squared theta, which becomes cosine squared theta, such that the square root of these two terms here, the square root of these two terms, square root of two terms cannot be simplified unless you can combine those two terms becomes one term. Then this will be 2 cosine theta. At the same time, if x is 2 sine theta, then dx will be 2 cosine theta d theta. Now with this substitution, then it works out to be integral of 2 cosine theta times 2 cosine theta d theta, where square root of 4 minus x squared becomes distinct, right? And the dx becomes distinct. Now, all of a sudden, what you have on the right hand here is integrable. So this is integral of, let me put the 4 out, and then you have integral of cosine squared theta d theta. And from there, you can go on further. Okay. Now, trig substitution actually deal with 3 type of things under square root. The one we have earlier just now, going back to the idea. Back to idea, then suppose I have square root of a squared minus x squared. Think about what should you substitute the x by. What should you substitute the x by? Such that, what is this? Such that a squared minus x squared is something a squared times some trig being squared. Such that the square root of that a squared minus x squared is a times that trig function. Okay, that's how we think that way. And then it's like, oh, you know what? If my x is a sine, if my x is a sine theta, then my a squared minus x squared will be a squared minus a squared sine theta, sine squared theta, which becomes a squared cosine squared theta, which when I do the square root, I get a cosine theta. Okay? Now, then, that gives us another thing. What happens if you see square root of a squared plus x squared? Now, what should you substitute the x by? What you substitute the x by such that a squared plus x squared becomes a squared trig squared. Then you remember 1 plus tangent squared x equals to secant squared, right? Okay, so if you have a squared here, you can have a squared tangent squared x here equals to a squared secant squared theta, right? Does it make sense? Okay, so let's substitute that x by a tangent tangent theta. Okay, because then if so, I will get a squared plus a squared tangent squared theta, which is a squared times 1 plus tangent squared theta. That's a squared secant squared theta. Under square root, it is a nice instead of addition under square root, that's not supposed to become one term. This becomes one term. The a squared becomes 1, well, because I factor a squared out. I factor a squared out. Just like here, I factor a squared out. Okay? Now then, so if you see a squared plus x squared, you need to be creative though. If you try to memorize from the book, it will take you longer time to actually get used to it. I prefer you to use your intuition. Okay, what kind of a trig equation substitution you can use for this? What kind of trig substitution you can use for this? Okay. Now, what happens if, on the other hand, I have x squared at the front? Square root of x squared minus a squared. So think about what is your x such that, x squared minus a squared give you a squared times 3 squared. And you will realize that the one we use is actually still that 1 plus tangent square theta equals to secant square theta. But the one we use is actually tangent square theta equals to secant square theta minus 1. So if my x is a secant theta, then my x squared minus a squared will be a squared secant square theta minus a squared, in which I can factor the a. I can factor the a squared. Then I get a squared tangent square theta. The square root of this gives us a tangent theta. Okay, now that's the idea for this section. The idea is actually quite simple, but you will see when we work it out, there's a lot of details we need to fill in. And that's what makes this section actually on the difficult part. Let's say, for example, I will start doing problems. Let's say, for example, I pick question from this 7.3, number 7.3, section 7.3. Number 8. We have integral dt over t squared square root of t squared minus 16. How will we do this? Well, we focus on this first. What should I do here? Oh, by the way, trig substitution may not mean that's the only way to do it. Okay, doesn't mean trig substitution is the only way to do it. Okay, but it just opens a door for a situation when it's not doable otherwise. So for example, if you have this question, integral of t square root of t squared minus 4 dt, I think we'll just use u equals to t squared minus 4, right? Because the u give you that t dt thingy. Does it make sense? Okay, but Thomas, in that case, can I use trig substitution? Yes, you can, but that's not the only way. Yes, you can, but that's not the only way. Okay, now let's go back to that question. So I need to think, what should t be such that t squared minus 16 under square root give me a nice number? Let my t be 4 secant theta, such that t squared minus 16 is 16 secant squared theta minus 16, which is 16 tangent square theta. I skipped one little step there. So square root of t squared minus 16 is equals to 4 tangent theta. Is it okay so far? Now, meanwhile, don't forget, if t is 4 secant theta, then dt will be 4 secant theta tangent theta d theta. It takes too much space. Let me do it underneath. So now using that substitution, then this integral now becomes integral of dt is 4 secant theta tangent theta d theta, that's for the dt, over t squared is 4 squared secant squared theta. The square root of t squared minus 16 is 4 tangent theta. Okay, simplify here and there, I get 1 over 16 integral 1 over secant theta d theta. Now, do you know how to integrate this? If you don't know, you must be thinking too hard. Yeah, it's cosine, right? So this is 1 over 16 integral of cosine theta d theta, which is 1 over 16 sine theta plus constant. Is it okay? But we are not done yet. We are not done yet because our integral was in terms of t, so our solution should be in terms of t, right? Now then how to change this sine theta back to terms of t? Do the triangle. T over 4 equals to secant theta. Draw the triangle that gives you that situation. If this is theta, then secant will be hypotenuse over adjacent, right? Then this will be square root of t squared minus 4. Are you with me? This technique is supposed to be taught in trigonometry, but also taught in pre-calculus. Okay, so what is sine theta here? What is sine theta in this case? It will be square root of t squared minus 4 over t. Right? Now that's what I will use underneath here. That will be square root of t squared minus 4 over 16t plus constant. Okay. Now, I do not recommend you to do this too early. Now, you can do it much later. This triangle thingy, the one in red, you can do it much later. Until you know what kind of trig function you need to substitute back to t. Okay? But the first step is your intuition, though. The first step is your intuition. Let's do more. Suppose I have number, let's do number 10. Let's do number 10. That's integral of t to the 5th over square root of t squared minus plus 2 dt. So we have t squared plus 2. What should my t be such that it becomes one term? That's square root of 2 tangent, right? Okay, so I get t squared plus 2 later on will be 2 tangent squared theta plus 2, which is 2 secant squared theta. And the square root of this guy now, using that substitution, becomes square root of 2 secant theta. Now, on the top of that, dt will be, the differential of t will be square root of 2 secant square theta, d theta. Now, we do the substitution. Apply the substitution. I have t to the fifth on top. So this is equals to integral of square root of 2 to the fifth tangent to the fifth theta dt is square root of 2 secant square theta d theta over, on the denominator we get square root of 2 secant theta. Square root of 2 cancels, so I get square root of 2 to the fifth outside. Integral tangent to the fifth theta secant theta d theta. How do you integrate this now? Now you know your 7.2 has to be strong. This is, I think I will do, well, this is 2, 4, this is 4, square root of 2, integral. I think I will do tangent to the fourth theta, tangent theta, secant theta, d theta. Thomas, how do you know that's what you need to do? I don't know. Experience. See, we would like to have secant square to help us with the substitution. But if our secant is an odd number, odd power, then I need another tangent to help me for the substitution later on. Okay, notice that I will write this as secant square theta minus 1, that's tangent square. Being squared, give me tangent to the fourth. Okay, and then I do u substitution, u equals to secant theta. Right, so du is secant theta tangent theta d theta. That becomes 4 square root of 2 integral u squared minus 1 being squared du. Ooh. Do you think it's fun? This will be 4 square root of 2 of 1/5 u to the fifth minus 2/3 u cubed plus u. Don't forget, it's constant. But this still equal to 4 square root of 2 1/5 secant to the fifth theta minus 2/3 secant cube theta plus secant theta plus c. Okay, I wonder if you are copying that down. Look back, because we are not done with theta. Our original integration is in terms of t. So let me use this. T over square root of 2 equals to tangent theta to the triangle If this is theta t square root of 2, this is square root of t squared plus 2. Now what is the secant of that? T square root of t squared plus 2 over square root of 2. Okay, then I put back here. This will be 4 square root of 2, 1/5 square root of t squared plus 2 over square root of 2 to the power of 5 plus minus 2 over 3 square root of t squared plus 2 over square root of 2 cubed plus square root of t squared plus 2 over square root of 2 plus constant. Distribute. This is 4 square root of 2 over 5. And then at the bottom here, I have 4 square root of 2 on the top here. T squared plus 2 squared square root of t squared plus 2 minus 8 square root of 2 over 3, and then I have 2 square root of 2. This is t squared plus 2 square root of t squared plus 2. Nasty, huh? Welcome to calculus 2. Plus 4 square root of 2 times square root of t squared plus 2 over square root of 2 plus constant. Yeah, the things, a lot of things cancels here though. So this is 1/5 t squared plus 2 being squared square root of t squared plus 2 minus that's 4 over 3, huh? Do you think so? Yeah, that's 4 over 3. That's 4 over 3 t squared plus 2 times square root of t squared plus 2 plus 4 times square root of t squared plus 2 plus constant. I really think you should try to simplify this even further. I think you should try to simplify this even further. Let's see, at least you see that I can factor that square root of 2. Not only you need to expand it all the way like that, you need to simplify that. Yeah, you need to simplify it. Because you see that, at least you see the following. Notice that from these terms here, when you expand, you will have t to the 4th and t squared and constant, right? Now, from this term here, you have t squared that you can combine with the t squared from there. The constant, you can combine with the constant there and also the constant here. Okay, so it may be better if I factor that t squared plus 2 out first. Okay, so I get 1/5 t to the 4th plus 4/5 t squared plus 4/5 minus 4/3 t squared plus minus 8/3 plus 4 plus c. Now then you deal with that expression inside the t to the 4th, nothing to combine, so t to the 4th by itself. How about the t squared? 4/5 minus 4/3. Negative 8 over 15. Plus 24 over 5. And if you want to do LCD, which I believe our textbook will do, if you do LCD, then it will be 15 on the denominator here. Okay, and then we will get 3t to the 4th minus 8t squared plus 72 square root of t squared plus 2 plus constant. Ugly, huh? But you see, our trig substitution actually done here. Our trig substitution is actually done here. Right? Anything from here and on, that's algebra. Okay, and this is only number what? Number 10. This is question number 10. Oh, by the way, this is not the only way to do it though. This is not the only, I know this looked ugly, I know this looked ugly, but this is actually not the only way to do it. Let me do it other way, other method, number 10, redone. Integral of t to the 5th over square root of t squared plus 2 dt. I can do this substitution, u equals to t squared plus 2. So du is 2t dt. Is it okay? Now I will rewrite this for now. I will get t squared being squared t dt, that will be for my du later on, over square root of t squared plus 2. Now then t squared will be u minus 2. Okay, now t dt will be du over 2. On the denominator, we have square root of u. See, it works very nice, right? Okay, so this will be 1/2 integral of u to u squared over square root of u minus 4u over square root of u. I'm sorry. I think I'm missing. Am I missing something there? No, I'm not. For square root of u plus 4 over square root of u du. That's integral of u to the power of 3/2 minus 4 to the power of 1/2 plus 4u to the power of 1/2 and then 4u to the power of negative 1/2. This will be 2/5 u to the power of 5/2 minus 8 over 3 u to the power of 3/2 plus 8u to the power of 1/2 plus constant. And then let me factor 1/2 u to the power of 1/2. So I get 2/5 u squared minus 8/3 u plus 8 plus c. Now substitute your u now. This is 1/2 square root of t squared plus 2, right? And then times 2/5 t squared plus 2 being squared minus 8/3 t squared plus 2 plus 8. then I FOIL, simplify the guy inside. So you see, I use two different methods, right? But neither one of them is nice. Just see. It's less messy without trick. Yeah, it happens. It happens in this case. Right? So it is actually true that if you can do it without trick, maybe it's better. I have that same opinion, but I have seen problem in which originally it seems to be nice until when I substitute it back, it's nightmare. So this becomes 1/5. No, I will distribute the 1/2 in, I guess, but let me combine like terms inside first. Let me combine like terms inside first. So this is square root of t squared plus 2, and then that's 2/5 t to the 4th, and then plus minus actually minus 1/5 minus 1/3 is 2 over 15, so 16 over 15 t squared. 24 minus 8 is 18, 16. Multiply by 2 in. I do it one step at a time. Okay, so multiply by 1/2 in, I get 1/5 t to the 4th minus 8 over 15 t squared plus 8 over 3 plus c. You get the LCD, 15. I get something different. My last one is here. Oh, sorry. This is wrong. 8/5 plus 8. I look at the wrong one. 8/5 plus 8, that's 48. That's 48 over 5. Oh, no, I'm too fast. See, it's too easy, right? I need to add this 8 over 5 minus 16 over 3 plus 8. Okay, so this is 24 minus 80 over 15 plus 8 times 15 over 15. That's negative 56 over 15 plus 100 over 15. What's that? 64? Yeah, 64. Do I make any miscomputation? Over 5 here, 16 over 3. Now the thing is when I divide by 2, this when I divide by 2, that becomes 32 over 15. But that's not what I get up there. How do I get that 72, by the way? Am I missing anything? Ah, I forgot to add that 4. See what I did here, this 4/5 plus 4 give me that 24. But this is not right. This is not right. Delete 4/5 minus 8/3 plus 4. That's 12 minus 40 over 15 plus 4 times 15 over 15. That's negative 28 over 15 plus 60 over 15. 32 over 15. Yay! I get what I need. So this is 32. At least now I show you that both methods give you the same answer. And which method is better? It depends on your experience. Sometimes, to be honest with you, sometimes it takes you more time to think about which method is better. Why don't you just start doing something? Okay. By the way, similarly, if you take a look on number 20, if you take a look on number 20, integral of x over square root of 1 plus x squared dx, of course, the first method you can do, the first method in relation to the topic we have here, you say let x equals to tangent x, right? I mean tangent theta. I cannot use tangent x. That's the substitution. But the second method, can you hear me, by the way?
Yeah.
Okay, because I start hearing some echo. Okay, so another way is you say u equals to 1 plus x squared. So du equals to 2x dx. Right? I think this method is actually better. So if I use the second method, this will be integral du over 2 at the on the top, and at the bottom I have square root of u. Right? And that's equals to 1/2 integral u to the power of negative 1/2 du. Is it okay? So actually, this is 2u to the power of 1/2 the plus constant. So that's square root of u, that's square root of 1 plus x squared plus constant. Duh, it's so easy. Well, don't get too fast. Suppose I use the first substitution. Suppose I use the first substitution, x equals to tangent theta. So, oh, why? I want to use red. If my x equals to tangent theta, then 1 plus x squared will be secant squared, right? Is it okay? And then the square root of 1 plus x squared is secant theta, while dx is secant squared theta d theta. Such that with that substitution, we get integral of x to be tangent theta. Okay, dx is secant squared theta d theta over the denominator is secant theta. That's equals to integral of tangent theta secant theta d theta. But what is the integral for this? Secant theta that's constant. Right? But then when you look at the triangle, tangent theta is x over 1. such that secant theta will be just square root of 1 plus x squared over 1 as constant. So you see, you have two different methods to do it. It seems like number 20 is a lot easier than number 10. Don't you think so? A lot easier. How about number 22? They have different color there. Number 22, we have integral from 0 to 1 square root of x squared plus 1 dx. No way, you have to use trig substitution here. There's no way to do this other way, otherwise you need to use trig substitution here. So I let my x equals to tangent theta. So my x squared plus 1 is secant squared theta. The square root of that is secant theta. While my dx is secant squared theta, d theta. Okay. And remember this thing, please, please, please. I don't forgive you if you don't do it this way. If you have a definite integral, and you do substitution, then you need to change the limit of integration at the same time. Okay. It is not appropriate to treat that with the as an indefinite integral first. No, that's not appropriate. Can I, Thomas? That's silly. It's like you substitute and then you substitute back. But put it this way. What is the reason you substitute this guy? It must be because he's ugly. Right? I mean, that guy is ugly. That's why you substitute him. I mean, even in real life, that's true. Right? You see somebody ugly as your boyfriend, come on, substitute. Right? And another reason is that person is not workable. Right? So once you substitute, why you want to get back to him? Huh? Dude, make up your mind. Once you say we break up, no coming back. So think about that hard before you break up. And make sure when you do substitution, you get something better, right? The silly thing is you substitute that and then you get back to that guy again. Right? There's always second chance. Okay, why you give second chance to the same person while you have so many chances with other people? After second chance, third chance, fourth chance. And then other people will say, you are not fair, you don't give me any chance, right? No, no. See, on the other hand, the reason you do substitution and therefore you change the limit of integration at the same time, so that it's actually easier to do it that way. When I look at the last quiz you turned in, some people keep on doing this, like you integrate that indefinite integral and then you change it back to x. You already substitute that x becomes u, and then you go back to your x. Okay, do you love your x so much? Huh? No pun intended. Okay, once you substitute, then that's it. Don't look back. Okay, so when x equals to 0, what is your theta? Theta equals to 0. It has to be in gradient, by the way. When your x equals to 1, what is your theta? Pi over 4. Now then your integral right now change at the same time. This is 0, this is pi over 4. Okay, this is secant theta. Dx becomes secant squared theta d theta. Okay, whoever your Calc 1 teacher who didn't emphasize that didn't do a good job. Okay, why? Because if this is your theta, if this is your theta, then the numbers here is for theta. Okay, you cannot say this, oh, you know what, Thomas, I will change the limit of integration later on. But that's not what it means though. If you write in this notation, it means this is in theta. Theta equals to 0, theta equals to 1. That's what it means. But you know, Thomas, that's not what I mean. I don't know what you mean. All I know is what you write. Okay, say what you mean what you say. Write what you mean what you write. Anything other than that is bias. Imagine if your teacher grade you based on that mindset. Oh, I think that's what you say. And then I mark you wrong instead of mark you right. You see what I mean? No, I can only judge you based on what you write though, not based on how much I know you. Yes, you will get your points deducted. Take a look on your test, on your quiz. Take a look in the comment. I return your quiz in the comment. What if you put on the integral x equal, what do you mean? What if you put on the integral x equal? Yeah, if the limit is for x, then you should not change this to theta. It has to be still x. Because by convention, the number you put here is for this variable. That's the convention. That's what it means. Okay, you cannot say that this is in terms of x, while the variable of integration is theta. No, you can't. If that's how your teacher taught you, go back to that teacher, say that's not right. You can open any textbook. None of them do it like that. Why is all of a sudden you say your teacher's okay to do that? Because that's your teacher? And because he actually or she actually let you pass? That's bias in true sense, right? Okay, somebody bought your vote. Don't you think so? No. I know what you mean, but when I grade you, I have to grade you based on what you write, not based on what I think you want to write. Okay. Now remember, I told you one person, Andre, was my former student. Okay, he did well. Okay, so in case that he wrote something wrong, will I say, oh, I know what he meant, he just wrote it wrong? No, I can't. I cannot. I still have to mark it wrong. Okay, of course, I don't mark it wrong, that totally wrong. I still give partial points, right? Okay, I'm sorry, Andre, I pick on you. No, I'm not picking on you. You know I like you so much. Don't be too harsh on grading. I try, but I also know one thing. When I learn how to teach, okay, I also learned that grading is one way to teach. So penalize you for something wrong, actually telling you that's wrong. Okay, but I still give you partial points. Don't worry about that. Don't worry about that. I still give you partial points. Now, then this will be integral from 0 to pi over 4 of secant cube theta d theta. How would you like to do this? Long time no see. The only way you have time to do this problem is by memorize what is secant cube. From last time I did it. This is equals to 1/2 secant theta tangent theta plus 1/2 natural log absolute of tangent secant theta plus tangent theta plus constant. Oh, I don't need constant because it's definite integral. From 0 to pi over 4. Oh, by the way, do you want to change it back to x? Do you want to change it back to x? Not yet. Well, no need, because you already have the limit in terms of theta. Don't look back. It's already in theta. There's no need for you to change it back to x. Okay? So I will just plug that in. What is secant pi over 4? That's radical 2. Tangent pi over 4 is 1 plus 1/2 natural log radical 2 plus 1 minus secant tangent 0. That's 1/2 times 1 times 0 plus 1/2 natural log of 1 plus 0. This is radical 2 over 2 plus natural log of square root of 2 plus 1 over 2 minus 0. Okay, so your final answer will be, radical 2 plus natural log of radical 2 plus 1 over 2. Ugly. Now, imagine if you insist, you know what, Thomas? My previous teacher taught me just do the indefinite integral first, and then you plug that in later. So the way you do it is you say, oh, even if you want to change it into indefinite integral, you need to declare that though. Consider integral of square root of x squared plus 1 dx. You need to declare that first. You need to define it first, that you are dealing with the indefinite integral, not with the definite integral. Okay, fast forward, then you will get this is equal to 1/2 secant theta tangent theta plus 1/2 secant theta plus tangent theta plus constant, right? But if you don't listen to me, then what will happen is you need to change it back in terms of x. So tangent theta equals to x. So this is x, this is 1, this is square root of x squared plus 1. Now, secant theta will be square root of x squared plus 1. Tangent theta will be x plus 1/2 natural log of, I use natural log. One-half natural log of square root of x squared plus 1 plus x plus constant. And then so integral from 0 to 1 of square root of x squared plus 1 dx equals to, I don't even want to write it down. 1/2 square root of x squared plus 1 times x plus 1/2 natural log of square root of x squared plus 1 plus x, and then from 0 to 1. Now the thing is, it means you need to bring it back to x, right? That's painful, as if this question is not painful already, right? Another way to say it, you don't like hard problems, but what you do tends to make it a lot harder. So do you like it hard or not? Make up your mind. If you like it hard, then do it hard way. And I give you a hard problem so that you can make it even harder. Not to say that this is actually big, long, and hard, right? No, you don't like it big, long, and hard in this case. In other case, yeah, fine, but not this one. Maybe I say seriously. Okay, but that's not my fault. Somebody didn't teach you right. Okay. No, once you do substitution for a definite integral, change the limit of integration right away so that you don't need to look back to that x. Okay. I'm about to do one hard problem. Number 16, it looks so messy. Which one you like? Which one would you like? Number 16 or number 18? I do only one of them. You tell me. One. One means one, not both. 18, okay. Number 18, integral of dx over ax squared minus b squared to the power of 3/2. Man, I should not let you choose, huh? I regret it. Okay, I need my ax equals to b secant theta, such that ax being squared minus b squared becomes b squared secant squared theta minus b squared, which is b squared tangent squared theta. Hence, square root of ax squared minus bx is equals to b tangent theta. On the other hand, the differential, let me just take space on the right hand side here, a dx equals to b secant theta tangent theta d theta. Okay, that's the setup. You will see that this, what I put in red braces here, is actually the crucial step. And organize it well. Don't rush back to the integration. No, don't rush back to integration. Anything wrong you do here makes whatever you do after that waste of time. Okay, so do it right. Some people ask me, Thomas, the way you write your test doesn't give me any chance to check my work. First, the time has something to do with your speed. Second, how about do it one time but do it right, instead of like telling yourself, how about second chance, right? You know, no, don't think that way. Actually, it's waste of time. That's waste of time. Okay, just do it one time but do it right, so that you don't need to look back. Okay, live your life in a way that's such that 10, 20 years from now, when you look back, you say, you know what, I really did my best and I didn't waste my time. Okay. Yeah, I'm not saying that you should not play. Well, you need some recreation. You need to play. Okay, you need to have fun, just to keep your sanity, right? But you don't play all the time such that you don't study. No, balance it. Okay, balance it. Okay, then let's come back. This is integral of my dx will be 1 over a, actually b over a secant theta tangent theta d theta. That's for my dx, right? My dx. Over this guy here is this thing, right? Okay, so now I have basically becomes b cube tangent cube theta. How about that? Now let me simplify. This is equal to 1 over AB squared integral of secant theta over tangent square theta d theta. How to proceed from here? This is 1 over AB squared. Let me change them into sine cosine. Who knows? This is 1 over cosine theta. This is sine squared theta over cosine theta. Cosine squared theta. D theta. Ooh. Oh, actually it's quite nice. 1 over AB squared integral of cosine theta over sine square theta d theta. Okay, so if my u is sine theta, my du will be cosine theta d theta. So that's integral of u to the power of negative 2 du. That's negative 1 over AB squared u. Ooh. Plus constant, Thomas. That's half point. Okay, let me continue here. At least I'm done with the integration. I just need to do the substitution back to theta and back to x. I think I already have the theta. Oh, that's in u. So sorry. That's equals to negative 1 over AB squared. The u was sine theta. But then when I look at the triangle, secant theta is ax over b. So this is square root of ax squared minus b squared. Now the sign of that is, so this becomes ax over ab squared square root of ax squared minus b squared plus c. Oh, so painful. This is negative x over b squared square root of ax squared minus b squared plus constant. Would you need to rationalize the denominator? No need. No need. You can just leave it like that. Okay, let's take a break. Right now it's approximately 8:40. We come back at 8:50. And then we will continue with some problems from here. Actually, there's a chance that, yeah, maybe I will do some more problems from here. There's a chance that I will okay, what I want to say is your test 1 will be up to 7.3, right? So I'm actually not in rush to do 7.4, and your test 1 will be 2 weeks from now, okay? But 7.3 is the crowning section for a lot of integrals at the back of the book. It's like with this one section only, with what we learned from this one section, you can do so many proofing at the back of the book. So what I plan to do is after this break, we do 1 or 2 more problems from this section, and then we look at the back of the book to do proofing. Okay, let's take a break first. Okay, let's start. We will go on with a couple more questions from this section before we pick some problems from the back of the book to prove. Number 24, for example, we have integral of dt over square root of t squared minus 6t plus 13. What we will do is we do completing the square at the bottom. So this at the bottom will get dt equals to dt over square root of t squared minus 6t plus 9 plus 3. I want to complete this t squared minus 6t. So I add 9, which I took from the 13. That should be plus 4. So this is integral dt over square root of t minus 3 squared plus 4. Now then, change your t minus 3. T minus 3 becomes what? The coefficient? Nobody say anything. 2 tangent theta. Okay, so dt later on will be 2 secant squared theta d theta. And then t minus 3 squared plus 4, that will be 4 secant squared theta, right? So the square root of that is 2 secant theta. Now put them together. So that integral now becomes integral of 2 secant squared theta d theta over 2 secant theta, which is integral of secant theta d theta, which is, now you don't have time to actually derive it again, memorize it. This is natural log of secant theta plus tangent theta plus constant. Then we look back, t minus 3 over 2 equals to tangent theta. In our triangle, if this is theta, this is t minus 3, this is 2, this is square root of t squared minus 6t plus 13. This is natural log of square root of t squared plus minus 6t plus 13 equals to 2. And this is t minus 2. Okay, well, by the way, this is the same to natural log of square root of t squared 6t plus 13 plus t minus 3 minus natural log of 2, which is a constant, right? So we can put this together and call that a new constant. Let's C star. Okay, so yes, it involves some completing the square there. Okay, next, number 26 or 28? Number 26 or 28, you choose. If you hear me, you have the right to tell me what to do. Hardly happen like this though. I don't like my student tell me what to do. Nobody does. Number 26. I hope I have enough space here. Number 26, integral of, you know what, let me just start a new column at the bottom. Integral so that I don't feel get squeezed. Integral of x squared over 3 plus 4x minus 4x squared to the power of 3/2 dx. You see the guy inside the parentheses is actually, we need to complete the square there. The thing is, how do we complete the square for that though? That's minus something. How about that? That's minus 4x plus 4x squared. What do you think? Right? I factor the negative. Oops. If I factor the negative, that's not what it looks like. If I factor the negative, it looks like 4x squared minus 4x. So what should I add or subtract? To complete that. I think I will add 1 here, right? And then I add 1 inside. How about that? So the 1 cancels, right? Okay. So this becomes integral. Oh, I missed my dx. Half point off here, half point off here. Good thing I didn't turn it in yet. Okay, so x squared over, so this is 4 minus 2x minus 1 squared to the power of 3/2 dx. Now, the substitution. 2x minus 1 be what? So you think of that as 4 minus blah squared. What should that blah be? Sine, close, almost right. Now don't forget you need to adjust with this. Okay, what will that be? right? 2 sine something. Such that when I do the differential, dx 2 dx equals to 2 cosine theta d theta. So dx is simply cosine theta d theta. On the other hand, then 4 minus 2x minus 1 squared will then be 4 cosine squared theta, is it right? So square root of that is equal to 2 cosine theta. That's the setup. Okay, let me continue the integration here so that I have some space on the right hand side later on. This is integral, oh shoot, that's x squared. What will that be? So 2x equals to 2 sine theta plus 1. X equals to sine theta plus 1 half. Ugly. Sine theta plus 1 half being squared, dx will be cosine theta d theta. Big over, at the bottom I will have 8 cosine cube theta. Which then becomes, let me pull that 1/8 out. One of the cosine cancel, so that's sine squared theta plus sine theta plus 1/4 over cosine squared theta d theta. Oh, this is actually not that bad. This is 1/8 integral of tangent squared theta plus secant theta tangent theta, is it right? Plus 1/4 secant squared theta. Oh, tangent is secant squared theta minus 1. So let me continue here. So this will be 5/4 secant squared theta plus secant theta tangent theta minus 1 d theta. Okay, that's nice. That's 1/8 of 5/4 tangent theta plus secant theta minus theta plus constant. Painful. And let's go back. I need to look at the triangle now. So sine theta is 2x minus 1 over 2. This will be square root of 3 plus 4x minus 4x squared. So the tangent will be 5/32. What's the tangent? 2x over that. So 2x over square root of 3 minus or plus 3 plus 4x minus 4x squared plus 1/8 of secant theta 2 over that minus, what is theta? Theta is sine inverse, huh? That theta equals to sine inverse of sine inverse of 2x minus 1 over 2 as constant. Okay, next, make it look nicer. That's 5x over 16 square root of 3 plus 4x minus 4x squared. Let me just put them together, plus 4 minus sine inverse of 2x minus 1 over 2 plus constant. So you see this section here, you need to be extremely patient. When I say patient, doesn't mean you're slow. Okay, practice your speed also, but at the same time, try not to skip steps, because the setup, especially this part here, the setup later on turns out to be very important when you need to get it back. Okay, you need to get it back. I don't think I make any mistake here, but I'll take a look just in case. It's so long such that if I make any mistake, I may not even realize that. Okay, I will pick a question from the back of the book. Pick a question from the back of the book. If you have your textbook with you, please take a look on reference page 6. Reference page 6. Reference page 6. Between number 21 to number 29, would you like to choose a problem? Now, there could be a problem we cannot do yet because we have not done with 7.4. But I think most of them are doable already. Nobody make a choice? Okay, I choose number 24. Reference page 6, number 24. The question is proof. I randomly pick a number. Proof that integral square root of a squared plus u squared over u squared du. You can change the u, all the u's into x there, and you're fine. Equals to negative square root of a squared plus u squared over u plus natural log of u plus square root of a squared plus u squared plus constant. we do this proof, I think I will make my u equals to a tangent here. So du equals to a secant squared theta d theta, and a squared plus u squared equals to a squared secant squared theta. I skip one little step here. And furthermore, square root of a squared plus u squared equals to a secant theta. Put it back. I get that's integral of a secant theta over u squared will be a squared tangent squared theta, and the du will be a secant squared theta d theta. Cancel this, cancel that. I get secant theta, secant squared theta over tangent squared theta d theta. The thing is, how would you like to do this? Let me make it into sine cosine thing. So I will get 1 over cosine cube theta on the top. At the bottom, I have sine squared theta over cosine squared theta. Oh shoot, it's not helpful, huh? So I still get 1 integral of 1 over sine squared theta cosine theta. Not a good idea. I can't do it from there. Even if I want to continue, it requires 7.4. So let me stop there. Okay, let's do other way. I think I will play around with that secant square. Which after distribution and canceling, I get integral of secant theta plus secant theta over tangent squared theta. That is integral of secant theta d theta plus integral of I think I get cosine theta over sine squared theta. You can check. But integral of secant theta is natural log of secant theta plus tangent theta, long time no see. Plus, if my u equals to sine theta, then did I use u? No, I cannot use u. Sorry, I cannot use u. Let me use w. Because I already have u originally, right? Okay, don't use u anymore. Let me say I use w. So dw will be cosine theta theta. So this integral becomes w to the power of -2 dw. this is natural log of secant theta plus tangent theta. 1 over sine is cosecant. Now I will put it back. U over A is tangent theta. So this is square root of A squared plus U squared. I get a message. Let me see. Why is it without a square? Let me see. Which is it? Not secant squared tangent squared. Okay, so let's take a look here. If I distribute this, if I distribute the top, right, then I will get secant theta tangent squared theta plus secant theta over tangent squared theta. Now the first part here becomes secant theta only. And this is the second part. Okay. Then I erase the last couple column. Where's my triangle? Where's my triangle? Up there. So secant will be, this will be natural log of square root of A squared plus U squared over A plus tangent theta will be U over A minus cosecant theta will be square root of A squared plus U squared over U plus constant. Now let me notice that this is not exactly the same to what we need. Okay. This guy is okay. This guy is okay. Now the thing is, what happened to this? It doesn't look like this yet. Why? Why, Thomas? Why? Well, because of the following. Let me write the second term first, just to match the position. And this constant here, let me call it C star. And then plus natural log of square root of A squared plus U squared plus U over A plus C star. Now the thing is, we know from the past that this is, I massage that a little bit further. Is it U squared? No, it's U, not U squared. Okay, plus natural log of square root of A squared plus U squared plus U minus natural log of A plus C star. But this thing gives you a new constant. But Thomas, something's still not right. Something's still not the same. What happened on the top here? That's a parenthesis. Ha 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 ha. That's a parenthesis. You see, Thomas, you get absolute value. It's different, Thomas. It's different. Oh, hold on. Don't be too fast. So whenever you have a definite constant, you can combine it with other constant for a new constant. That's right. C1 plus C2 equals C3. It's a constant anyway. Now then, the argument will be as the following. Notice that square root of a squared plus u squared must be greater equals to the square root of u squared. Is it right? Which is equals to u. Now notice that this u may be positive, may be negative. This u may be positive, may be negative. So if I subtract by u, suppose u is positive, right? That will be positive. That's still greater than u. Now, if it's negative, if u is negative, then the whole expression becomes even larger. It's okay? Where u can be positive, negative. Okay, so square root of a squared plus u squared plus u for sure is greater equals to 0. Now, such that the absolute of a squared plus u squared plus u must be equal to square root of a squared plus u squared plus u without parentheses. Seriously, Thomas, you even pay attention to that absolute value? Yes, when you say proving, no room for difference. That justification is actually not too hard to justify though, but you still need to write it down. Okay, what enabled you to change that absolute value now becomes parentheses. Well, because we then realize whatever the expression inside that absolute value, it will be positive in any way. Do you want to choose more? We have not learned partial fraction decomposition from 7.4. We have not learned that. So there could be a chance that I cannot really do some problems that we randomly choose from here. But most of them will be quite basically what we have. Anyway, I have approximately 20 minutes left. Let me go to suggested homework 7.3. Your suggested homework from 7.3. Maybe number 1 to number 49. Okay, and then number 39 is actually a good question to think about. Okay, so you do it by trig substitution first, and then you think about the interpretation in part B. Let's do the odd ones. Should be good enough. Okay, let me go on. 7.4. I cannot finish this for sure. This is quite a long section too. But from this long section, we will see some pattern such that we don't need to repeat doing the same pattern of these 4 cases. There are 4 cases. The first one is the case of distinct linear factor. Distinct linear factors, that's for case 1. Case 2, linear factors with repetition. And then case 3 is irreducible quadratic factor. Let me say distinct irreducible quadratic factor. And the last one is irreducible quadratic factors with repetition. Okay, let me give you some idea first, what we will be doing here. Idea. Suppose we want to integrate this thing. Let's say I want to integrate 3 over x squared minus 3x dx. You can do substitution here. Okay. In fact, there's nothing in the techniques that I have taught you can be used to solve this. Maybe you can do, maybe you can do trig substitution by first completing the square. Yeah, but that will be quite painful. The plan is the following. The plan is, can we break this 3 over x times x minus 3 into something over x plus something over x minus 3? Now, this is what we call partial fraction decomposition. You decompose that into the sum or difference of rational expressions. Okay. Now the good news is the following: if the denominator is linear factors and they are distinct, right? So x without the square, x minus 3 without any power. So if you have that situation, then it must break into x and x minus 3 on the denominator for sure. And the numerator must be 1 degree less than that. In other words, the numerator must be a constant here and a constant there. Now, what we did in the past in pre-algebra and in algebra is to move that way. If you have 2 rational expressions, when you add them, what happened? Right now, we decompose that instead. Is it okay? Now, that's what we want to do. Again, one of the key steps is you need to factor it, and hopefully each one of them without exponents, such that it must be this guy and this guy. Now on the top must have a degree 1 less the degree at the bottom. Now the degree at the bottom is degree of 1, so the top one must be constant. The degree at the bottom is 1, then the degree on the top must be constant. Now the thing is how to find that A and B. How to find A and B. Okay. Now let me go back to this. Once we get A and B, then this integral can now be written as A over x plus B over x minus 3 dx. Then each one of them can be integrated. That's A natural log of absolute of x plus B natural log of absolute x minus 3 plus constant. Is that right? Okay, so the bottleneck will be how to find the A and B. You see what I mean? Now, when you do the partial fraction decomposition, separate that. Like do it kind of like do it aside, okay, without the integral. How to find the A and B? What I will do is I will multiply each side by, each term by the LCD, multiplied by x times x minus 3. So I will get 3 equals to A times x minus 3 plus bx. Now, from here, you get two different methods. The first method seems to be more complicated at the beginning, but for the later case, this method is actually better. Let me call that method as like terms. Like terms method. So basically what I do is I distribute on the left hand side and then for the like terms I put them together, so A plus B times x minus 3a. Then from here we see you match the left hand side and the right hand side. You see the x term on the left hand side. The x term on the left hand side is 0. On the right hand side is A plus B. I think of this as 0x plus 3 here. Okay. And then for the constant term, you will get 3 equals to negative 3a. Now solve this system of equation. You will see the A is negative 1 and the B is 1. Therefore, 3 over x times x minus 3 equals to negative 1 over x plus 1 over x minus 3. That's the partial fraction decomposition. Okay, now once we get that A and B, I can put it back here now. So my A is negative 1, my B is 1. Make sure you keep track of your A is the numerator for X, and your B is the numerator of X minus 3. Okay, now then, oh, you know what? I can combine these two logs here. This is natural log of X minus 3 over X plus C. But the last two steps in red are two steps that I believe at this point you can do on your own. The problem is how to find that A and B here. Now, the first method I teach you is like terms method. Basically, you do distribution, you simplify, and then you match the term by term on the left and on the right-hand side. Okay, the X terms, the constant term, then you create your system of equations that you need to solve simultaneously. Sometimes it's actually quite easy by just looking at that, like what I did here. But at times you need to work a bit harder. Now, the second method is a method that is, I think our textbook doesn't teach that explicitly, or didn't call that with special name. I will call that with special name. Okay, and that special name is special value method. Special value method. 3 equals to A times X minus 3 plus D times X. Is it right? Okay, now I will not subdistribute it. I will just leave it like that. Now the thing is, I need to find A and B that works for every X. The key word is it works for every X. Because you need to have this equation to be true for every X. For every X, the AB has to be constant. In this case, the A is -1, the B is 1. Okay, it has to work for every X. Now, because it has to work for every X, then it has to work for any choice of X, right? Now, so if you choose X equals to 0, what will happen? 3 equals to A times -3 plus 0. So A is equals to -1. If you choose X equals to 3, then you get 3 equals to A times 0, which is 0, plus 3B. Right, so B equals to 1. Well, Thomas, how do you know you choose 0 and 3? Now think this way. Think this way. What will make this 0? What will make this 0? It works for every X, remember? It works for every X. If it works for every X, then choose an X that kill a term. That's actually you call that the secret, but that's the idea. It works for every X. So choose your X that kill a term the earliest. Okay, so you see here that whatever I have originally is something I get down here. Let's see number 10 in our textbook. Number 10, integral of y over y plus 4 2y minus 1 dy. Now I focus on the partial fraction decomposition. y over y plus 4 times 2y minus 1, because the denominator are linear factors without repetition, without exponents. I mean, the exponent is 1, then the denominator can be safely said, I mean, it must be y plus 1, 2y minus 1. And the numerator must be a constant and a constant, 1 degree less than the denominator. If I multiply by the LCD, then I will get y equals to a times 2y minus 1 plus b times y plus 4. Let me use technique number 2 right away. Okay, so when y equals to -4, that will be -4 equals to a times 2 times -4 minus 1 plus 0, right? That's the reason I chose -4. So -4 equals to -9a. So a equals to 4 over 9. Now when y equals to 1/2, why 1/2 times to make this 0? Okay, when y equals to 1/2, then the left-hand side y, will be 1/2 equals to 0 plus b times 1/2 plus 4. Okay, so 1/2 equals to 9 over 2b. So b equals to 1 over 9. So the result of that partial fraction decomposition is y plus 4, 2y minus 1 equals to 4 over 9 y plus 4 plus 1 over 9 2y minus 1. Hence, the integral of y over y plus 4 to y minus 1 dx is equal to integral of 4 over 9 y dy over 1 plus 4 plus 1 over 9 integral dy over 2y minus 1. Yes, it should be dy. But then the first integral here, this is 4 over 9 natural log of y plus 4. That's easy, right? Plus 1 over 9 times 1/2 natural log of 2y minus 1 plus constant. Okay, so with that said, let me ask you to do suggested homework for this 7.4a. You should be able to do number 9. Actually, you can do number 7 also. Just divide it first. Number 9, number 11, number 13. Yeah, but for number 7, let me give you the hint how to do it. Integral of, if the rational expression is improper, in other words, the degree on the top is greater or equals to the degree at the bottom, then what you will do first, you divide. So x to the 4th divided by x minus 1. Okay, so you will get, this is plus 0x cubed plus 0x squared plus 0x plus, plus 0. This is x cubed, that's x to the 4th minus x cubed. When I subtract, I get x cubed plus 0x squared so on and so forth. Let me just do it. That would be plus 1. So this is 1. So if the degree on the top is greater or equals to, then you divide it. Now you get x cubed plus x squared plus x plus 1 plus 1 over x minus 1 dx. And then you can integrate that. In the last case, y had the same degree as the denominator. Which last case? Number 10 you're talking about? I don't think so. Number 10, the degree on the top is 1, the degree at the bottom is 2. Yeah, this is the degree of 1, this is the degree of 2. Right? Okay, so then we cannot divide. It's already proper. It's already proper. Okay, well, anyway, that's for today. Work on this. And then on Monday, we'll finish up this 7.4 and work on 7.5. 7.5 is heavy, very heavy, very heavy. I think there were 1 or 2 questions there I myself could not do. But I don't look at the solution though. Don't rely on solution manual. I know some of you say, oh, you know what, Thomas, I have solution manual, and with solution manual next to me, I'll be fine. Oh, you don't have solution manual for my test. That's the thing. Okay, you will have the solution manual for my test at the end of the semester, but not right now. So it's more about the idea though, how you play with the integrals. Okay. Okay, that's for today then. See you.